Any questions regarding this classical discrete circuit bias arrangement? Look at the section, it is 1.1.5, and also you can have a look into the syllabus also. Okay, I just want to show the syllabus where what we are doing. This is the first topic. You can see the classical discrete circuit bias, which is also called as voltage divider bias. This is where our syllabus commences for module 1, and we are covering only BJT related aspects as of now, but later once we understand the biasing circuits related to BJT, we will cover even similar things with reference to the Mosfet. Okay, so I hope we are in track with the syllabus. Okay, now let me move directly on to this. This is the topic of today's class. Last class we introduced about this, what is this classical discrete bias circuit. Okay, we also discussed about few not good biasing schemes. Okay, so what are those biasing schemes? Anybody can recap? Okay, earlier biasing schemes before we jump into this.
Fixed VBE, fixed IB.
Yeah, one is fixed VBE. This is the first biasing scheme. In fact, the textbook commences with like this. Okay, so those syllabus started from classic discrete, starts from biasing by fixing base emitter voltage. We have seen the drawback of this. Anybody can tell me what is the drawback of biasing by fixing VBE?
Small change in VBE can affect IC.
Yes, because IC, the collector current and the base emitter voltage, this current and the base emitter voltage, they are related in an exponential manner like this. IC is equal to IS times e to the power of VBE by VT. Any small change in VBE, because this is an exponential term, base emitter voltage, small change here makes a big change in the collector current. But in biasing, the big changes should not happen. Okay, so always the output DC current, especially the collector current, should remain constant. AC current can vary, but DC current, collector current should remain constant. But here the problem is, since base emitter voltage depends on various other parameters also, small change, as I have given example here, 0.5 to 0.6 or 0.5 to 0.55, a small change in that makes a big change in the DC collector current here. So that changes we don't expect here. Okay, that's one of the major drawback of this biasing by fixing VBE. Next biasing scheme, which is bad biasing scheme once again, is by fixing base current. Any drawback of this we have discussed last class? Anybody can tell me what is the drawback of this circuit? Circuit is
as beta changes, yes, output current changes.
Yes. So previously the collector current was depending on VBE, but now let us assume that we are providing constant VBE by having constant base current here. Okay, so now the problem is with transistor BJT. When transistors are manufactured, bipolar junction transistors, they are manufactured in a lot. We don't manufacture one or two transistors. Okay, millions and billions of transistors are manufactured, and beta of those transistors, what is beta? Beta is nothing but a current gain of BJT in common emitter configuration. Okay, so the beta of this transistor among millions of billions of transistors that are manufactured, every transistor will have a unique value of beta. Okay, that means even though the bias circuit is same, just by changing this transistor, this BJT with another transistor, what will happen? So the collector current keep changing, right? One transistor may have say beta value of say 100, another transistor may have beta value of say 200. What happens? From 100 to 200 you see a big difference, right? So this change in beta value from one transistor to another transistor changes the collector current to larger extent here. So DC collector current here is, though we have provided constant base current to the input of BJT, but collector current now depends on the BJT beta value. okay, because you have already come across the expression, okay, so which is IC, you can see this expression IC is equal to what, beta times IB. This expression is quite popular, right? Okay. So, though you maintain constant beta value, so IB value, but the change in this beta value between the transistors, okay, manufactured by, even though the manufacturer is the same, but since the beta for two transistors differs, the collector current also keep changing. So, it is one of the major setback in this kind of biasing scheme. Now, you understood the problem of these two biasing circuits. One is by fixing VB, another biasing scheme by fixing base current. What are the drawbacks? Now, let us try to overcome that by using another a better biasing scheme. And we also discussed earlier class with an example with two different values of beta, how exactly the transistor moves from active mode to saturation mode we have seen. In this you can see that is the problem we have discussed in the last class. So, the transistor is an active region, okay, because collector emitter voltage which is given as 7.5 volts, that is far greater than the base emitter voltage here. So, therefore, this is in the active mode, active region, okay. And we have established proper the bias currents and bias voltages for this circuit. And again we worked out same problem for different value of beta. Here initially we have taken beta as 100, later beta has been changed from 100 to 200. We can see the next part of the problem is beta has been changed to 200, you can see here, and you see the condition of a transistor for that. When everything remains same, when beta is changed, the collector emitter voltage you can observe here, that has moved from a 7.5 volts to 0 volts. So, when the collector voltage changes from higher voltage to lower voltage, slowly transistor shifts from active mode of operation to saturation mode of operation here. We know that when transistor shifts from active mode to saturation mode, transistor cannot be used as an amplifier, right? We have seen that in the transfer characteristics. When we want to use BJT as an amplifier, it must be operated in the active mode or active state. For that condition is collector emitter voltage must be greater than the base emitter voltage. But here in this problem, since beta changed from 100 to 200, that made transistor to move from active state to saturation state. Many times even if you make the beta as a constant, even for some reason if temperature changes, then also the collector current keep changes. That is the point we have highlighted here. You can see here IC increases by 9% per degree Celsius change in temperature here. Okay, so there are a lot of parameters are there in the circuit, for especially the BJT, which disturbs this collector current here, DC collector current here. The bias circuit that we design must provide stable collector current here. But as we said already, one is beta, another one is temperature. Okay, like this, there are many parameters that changes the output collector current here. And I given one example also. Suppose if circuit is operating at 25 degrees Celsius, at 35 degrees Celsius, you can see that these two values will get double. Okay, so that means change in temperature is 25 to 35 degrees Celsius. Okay, even everything is you might have designed for 25 degrees Celsius. 25 degrees is nothing but a room temperature. Right now, currently the room temperature is 25 degrees Celsius. Usually in summer, the temperature rises from 25 to 35 degrees Celsius. Even though the bias circuit is same, because of change in temperature from normal room temperature to say summer, which is 35 degrees Celsius, look at the value of beta and IC. Okay, so beta and IC roughly they get double, even though the initially you design with fixed beta, but the gain varies and the collector current, DC collector current also changes. That means BJT will not be longer in the active mode, it will move into the saturation mode here. Okay. Now, the problem we highlighted last class here. So, IC and VC they are nothing but the operating point, and even if you fix the base current here, somehow they are directly proportional to the IB and IC, they are directly proportional to each other. and in fact IC is also related to the VC. We have seen that through Kirchhoff voltage law. So now these things are, since they are proportional to the beta of a transistor, we must establish a constant collector current even though the beta changes here. Okay, so the solution I have given here, what is the best way to maintain output DC collector current constant. To start with, you have to assume some constant DC collector current and work out backside. So far we have seen that input parameters how they are changing the output collector current, but now you have to come little reverse. You have to fix output collector current and see, go back and try to establish conditions for active region of operations, and also maintain proper resistors such that BJT remains in the active mode of operation here. One such a good biasing scheme that is as per our syllabus is the classical discrete circuit bias arrangement. What do we mean by discrete circuit bias arrangement? That means this circuit are not designed from integrated circuit point of view, IC point of view. Okay, they are the discrete circuit. Okay, so individual circuit we are discussing here, BJT based circuit we are discussing here. The classical means it's a very old fundamental biasing arrangement that we are discussing in this topic. Okay, so the circuit is as shown here. We have discussed many things in the last class. So there is a resistors which R1 and R2, as you can see. I'll just remove this. Okay, anyway, this is not working out, it seems. Okay. All right, this is the there are two branches in this scheme. There are two. I can split this circuit into the two parts. As you can see, you can think of this circuit like a two lines which are parallel lines here. Okay, one line is this, another line is this, like that. In one of this, the branch, you can see resistor R1 and R2, which uses power supply VCC. Initially we don't ground this, just for applying Thevenin's theorem we ground this. Okay, otherwise we don't ground this intentionally. Another branch what you are seeing here is contains the three components here, a resistor RC, BJT and RE. When we say three elements are there in this branch, there is a equivalent voltage drop also. So you can see here some the supply voltage VCC that is given here from this point to the ground here, that gets split into three parts here. One part get drop here across RC, another part of voltage drop occurs across collector and emitter of this BJT. This is a flower bracket as shown here. There is another part of this supply voltage get drop across this. So drop across RC, VCE and RE will be equivalent to the supply voltage. Similarly, in this branch, drop across R1 and R2 should be equal to supply voltage. Okay, so there are two independent branches here, you can see here. Okay, so this second branch what we are showing here with R1 and R2 is required to provide constant current to the base of this transistor, so that collector current is also maintained constant irrespective of the variations of transistor beta, temperature variations and lot of other parameter variations, alpha, beta, gamma, so many parameters are there. For a different transistor those values will also differ. So irrespective of the change in the transistor parameters, we have to maintain here the constant the current here, so which is IC. Let us label this as IC. So this is DC collector current we have to maintain constant. Okay, so now this circuit is very difficult to analyze if you have a branch like this, voltage divider like this. So we can simplify this circuit further by applying Thevenin's theorem. Thevenin's theorem can be applied by calculating voltage at this point. The node you can see here, which I am highlighting through the this color. You can see here. This is the so this is a node which you can see here. And at this point, if I label the voltage as VBB, okay, so the expression for this how do you obtain expression for this? Forget about this branch, and only for this branch, if I ask you to find out voltage at this point, you can use network theory concept and apply voltage division rule here, and you can find out voltage across this. Voltage at this point is nothing but voltage across R2. So now if I ask a question, if I have a circuit like this and I ask you to find out voltage at this point, let me remove this ground here. Okay. So here let me use a resistor here, this resistor, and here I will connect it to the VCC. Okay. Now what is the voltage here? If I call this voltage as VBB and this is equivalent to V Thevenin, since we are applying Thevenin's voltage, I can also label this voltage at this point as V Thevenin. Okay. Now what is the expression for voltage V Thevenin? So now voltage across this R2 or VBB or V Thevenin is equal to supply voltage times VCC times the resistor value R2, okay, resistor, and this multiplied this divided by R1 plus R2 here. Okay, that's how we can calculate the voltage across this point RTH. Okay, so 1 minute. Okay, so I hope you understood how to apply voltage division rule and find out the Thevenin's voltage at this point VBB. Okay, it's very simple. This is voltage division rule. Everybody is familiar with this voltage division rule. I hope you have done this in many times in network theory, right? I don't want to go back and find out. There are two rules which in network theory everybody should get familiar. Anybody can remember what are those rules? One is VD voltage division rule. Let us call that as VDR. What is another rule? Anybody remember?
Current division.
Current division rule. Very good. Exactly. So these are the two rules which you must remember in network theory. Even in competitive examinations, or the like a gate and several such examinations, they usually give a network like this and ask you to find out voltage across this. Here I have not given any value, like collector supply voltage value I have not given to you, and R1 R2 also is not given. Just I am finding the mathematical expression of what by applying Thevenin's theorem here. So which I got it as a simple rule is, when you want to find voltage across any resistor like this R2, take supply voltage and multiply with the resistor value of which you are calculating the voltage, and divided by sum of the resistor values. So same thing I did here, you can see here. Okay, so this is the formula for voltage division or Thevenin's voltage here. In examination, nobody asks you to derive this expression for VDR or CDR. Just go by shortcut method if you know that. Okay, same thing we have done in this topic also. Similarly, you can also calculate R Thevenin. R Thevenin, when you are calculating the DC voltage, must be grounded. Just remove this DC voltage which we have considered during applying Thevenin's theorem, Thevenin's voltage. Now what you do is just let me write original circuit here, resistor here R1, and now I will ground this. And now looking at this point or node, what is the resistance? Equivalent resistance. These two will become parallel resistors, right? R1 parallel with R2. So R1 parallel with R2 is nothing but product of R1 into R2 divided by sum of this resistor R1 plus R2. Okay, so these things you should remember here. So we got to know the equivalent of this circuit, complete circuit equivalent here. Okay, equivalent is a voltage source which is V Thevenin in series with the resistance R Thevenin. We have also labeled this R Thevenin as RB also. Do not get confused with too many names here, since I have to go by textbook method. Since in textbook instead of R Thevenin we use RB. RB and R Thevenin both are same. Likewise, instead of V Thevenin we have VBB also. So that's why too many things you may get confused. So that's why remember anyone. So now as per the textbook, VBB is nothing but V Thevenin, that is given by this expression VCC into R2 divided by R1 plus R2. R Thevenin, which is also equivalent to RB, which is R1 parallel with R2, the expression for that is R1 R2 divided by R1 plus R2. Now we got to know the equivalent of this, which is a voltage source, which is shown here, and resistance in series. Next circuit that I am showing to you is exactly the same. You can see here there is a VBB, same expression we derived here, and there is a resistance which is RB, R1 parallel with R2, and of course the remaining circuit, the second parallel branch is retained as it is. We are not changing this bias circuit, this is kept as it is, only the input side we are changing, that's all. I also told you the advantage of by simplifying voltage divider network to the network based on Thevenin's voltage and Thevenin's resistance here. Since in the circuit here it's difficult to analyze the operating point, and and also difficult to find the currents and voltages when there is a parallel branch like this. So that's why we have to simplify this parallel network into the individual voltage and series network, series resistance network like this. So now this becomes easy for us to analyze. Okay, so how do we do that? Next we apply KVL and try to find out the operating point of this transistor, and also we will see that whether this the inclusion of this resistance RB RE emitter resistor, this emitter resistor is also called as a feedback resistor. This resistor introduces feedback, so that means this having this resistance here, this provides signal back to the input, and whenever there is a change in VB for some reason, this increases or decreases appropriately. Now this having this RE is very important, this because this maintains a stability in the circuit here. Okay, stability in the sense, earlier without RE we have seen that, right? Even by fixing VB, how my DC collector current was changing, and with even base emitter voltage fixed, but IB when it is fixed, and we have seen even due to the change in beta how our collector current was changing. But now see, very simple change what we have done here is by adding a resistor RE, rest all things remain same. This network even earlier also we had, but here the extra thing what we have added is RE. RE is called as a resistor that maintains stability in the entire circuit here. Okay, see some small resistor how it adapts according to the changes. Okay, in electronics, see, research is very simple. Only thing is, see, by addition of this makes a very good circuit. Otherwise this, without absence of this, we called as a bad biasing scheme, right? See, if you remove this, the biasing is very bad, and by adding this the biasing has become very good. Okay, now we will see the advantage of this, how this resistor RE improves the stability in the circuit shortly. Okay. All right, now let us go through little bit mathematical aspects here. One more thing I want to remind all of you here, this analog circuits or analog electronic course, which this is a core course for electronics and communication engineering students, and even the telecom students also. Here students, what they tend to do and what is important, I just want to brief all of you. This is not like a mathematics, this is also not like a theoretical subject. Okay, most of you see, once you study a theoretical subject, you will remember, you will by heart, you will remember keywords, and you will write same thing in examination. But in mathematics also you practice the few problems, and similar problems will be asked in examination, so that it will be easy for you to do even the unknown problem asked in examination, because you have solved many similar examples in the classes. This subject is unique compared to the theoretical subject and mathematical subject, because this is a combination of both theory and problems. Okay, so you may ask a question, why we introduce the problems? See, this topic previously what I have discussed here, I would have discussed straight away with this theoretical aspects, right? But why I have taken this as an example? The reason is, if you want to understand this concept what we have learned in theory, the examples are very important here. So every theoretical topic should end with an example. Okay, then only you understand the theoretical topics very well. Otherwise, it becomes like a fully theory or fully mathematics. Don't only focus on problems. Don't only focus on theory. Both combination of theory and problems are required. Even in examination, also 50% of your question paper contains numericals and 50% contains theory. You can't only depend on theory and score from the theoretical topics. So study both together. Okay, that's why every topic you have going with the mathematical equations, and later I am going to solve a problem based on that. Okay, that's what I want to highlight at this point of time. Let's move on to the next thing here. So we know now supply voltage here, though we show here with an arrow mark like this, everybody should interpret like this. Okay, we have a that power supply, how do we indicate, right? One with long line, other one with small line like this. What kind of voltage it is? It's a DC voltage, right? Okay, it's a cell, right? The symbol, what it shows in electronic, if I show with line like this, one with long line, one with small line, and this is a cell. What if I show like this? You might have seen these kind of symbols even in electronics. What is that? What is the difference between this single long line and small line, and there is multiple long lines and small lines here? This is a battery, right? Yeah, this is a battery, right? It is a battery, and this is going to be a cell. Like this, many cells together makes a battery. Okay, so here for our simplicity, we have shown that with an arrow mark here. So students should not confuse with arrow mark if I write like this. So this is now equivalent to this battery. Okay, so here also you can see that it's equivalent to the battery. Okay, so this is the symbolic notations which everybody should be familiar. AC signals we show with circle like this. Okay, we will write a circle like this, and if I write here sinusoidal here, that shows AC. Sometimes AC also may have DC, right? That we show like this. Okay, this includes both AC and DC. If I show purely the sine wave inside that, it's a pure AC. Okay, in practically you cannot have pure AC like this. Every AC will also have some DC. Okay, that's why in amplifier circuit we use capacitors to eliminate DC. Okay, this is an AC plus DC. Understand? But we assume that incoming signal that we apply for this bias circuit is purely AC. So sometimes if DC is coming, we should eliminate that incoming DC with this capacitors here. We don't want any DC signal come along with AC, because this already we have established some voltages and currents. Any signal, DC signal coming with along with your AC, that should be filtered out here itself. Otherwise, that will change the biasing conditions of a transistor. Alright, so these are the fundamental things which you must be aware of it. So now let us proceed further. Thevenin voltage expression is shown here. Thevenin resistance expression is shown here. Okay, which we have labeled, instead of calling here as V Thevenin, we are labeling here as VBB. VBB also can be understood as base power supply. This RB is base resistance. Equivalent resistance at the base of a transistor is R1 parallel with R2. Okay. Next, let us go through the fundamentals. We know that for any transistor, there are two types of BJT. What are those two types of BJT? Two types of BJT. Yeah. One is NPN, other one is PNP. Which one is quite popular? Anybody can tell me among these two?
NPN.
What may be the reason? Why NPN? I may ask same question with reference to Mosfet also. Yeah, anybody has answer?
Both the current and the whole flow are in the same direction. directions are in NPN, so it's easy to analyze.
Okay. How about PNP?
Opposite direction.
Yeah. See, from understanding a point of view, a beginner, if any beginner wants to understand about BJT, we usually suggest start with PNP. But when it comes to the practical applications, we always prefer NPN. Okay. Same with even MOSFET also. Okay, you might have seen MOSFET devices. What are the different types of MOSFETs? Though we have not covered here, from electronic device fundamentals, I am asking different types of MOSFET.
N channel MOSFET and P channel MOSFET.
N channel and P channel. P channel. Again, question is which one is popular in this, and reason is why. Anybody has got answer? Just like here in BJT we said, right? Reason why I told you beginner should always learn PNP first, because here PNP majority charge carriers are holes. Current direction is also same as hole direction, so you will understand better PNP. If a beginner start studying the BJT using PNP. But NPN is little difficult for the beginner to understand, because here the current direction is different and electron movement is just opposite of it. There are chances of confusion is very high if you start with NPN. Okay. It's like a driving, that if I initially, if anybody wants to drive a four-wheeler, you should start with always in a small vehicle. I can't give a truck to you and ask you to drive it. What happens? You will just generally you will feel difficulty in driving that. Same way as here also. Look at here, this N channel and P channel. Again, to begin with, to understand the fundamentals, start with P channel. Okay, but later on you can start studying N channel, because there is just reverse in the operation of N channel and P channel. Okay, once you understand any one of these device, understanding is very important. Then other will be easily understood. With that fundamentals. Okay, now let us see, for any transistor either NPN or PNP, this rule holds good. Emitter current will be equal to what? Sum of collector current and base current here. Okay, I am not saying it is for this equation is valid only for NPN or PNP. For both the transistor, this equation is valid. Now we know that IC is equal to beta times IB, right? This is very popular equation. The collector current in a common emitter configuration is equal to beta times the base current. Now we can substitute this here in place of IC. Look at now, the emitter current now will be equal to IB plus beta IB. IB can be taken as a common factor here, and we got emitter current is equal to IB into 1 plus beta. And let us retain IB on right hand side and transfer rest of the terms to the left hand side. The final equation for base current is emitter current divided by the 1 plus beta. This is required for our analysis. That is why in the beginning itself we got the equation, we derived the equation for base current in terms of emitter current and the transistor gain in common emitter configuration. Now let us find the emitter current by applying Kirchhoff voltage law for the base emitter loop, which is labeled as L here, which you can see here. This is a loop. You can apply from here supply voltage all the way up to the ground. Okay, so you can apply KVL in this loop. Apply, when I say apply KVL, the source is here and ground is here. Start with this point and end with this point. Now we have a voltage here, which is arrow mark shows it is a VBB, and this is the way it is connected here. Okay, so you can see here, now we can apply KVL to this. I hope everybody is familiar by how to apply KVL. Okay, this subject C uses network theory concept and sometimes mathematical concepts also. It's a combination of several subjects that is there in this course, electronic analog circuits. Fine. So now what is the equation for KVL when you apply to the base emitter loop? So here is a base terminal and this is an emitter terminal. Therefore, this loop is called as base emitter loop. In fact, there are two loops are here. One is this loop starting from supply to ground. Another loop is collector emitter loop, which you can see there is supply here, even here also, and there is a ground. This line shows there is a collector emitter loop. So first let us apply voltage law KVL at base emitter loop and find out the equation for that. Here is a expression once we apply KVL to the base emitter loop. Start with this minus VBB plus drop across this RB is the current times the resistor value, which is IB times RB, and here we have a voltage drop, base and emitter voltage drop VBE, and plus drop across this emitter resistor RE. I started my journey from here and ended up at the ground, and along the path the voltage and IR drop must be considered. There are two voltage sources, one is VBB and other one is VB, as you can see in this equation here, and there are two resistors, one is RB, which is in turn R1 parallel with R2, and other one is RE, emitter resistor. So the drop across these two resistors must be considered so that the KVL is appropriately applied here. Okay. So IB times RB, that is the voltage drop across this RB, and IE times RE is the voltage drop across this. Generally, if you observe this equation here, there are two currents, you know that one is IB, other one is IE here. Now let us find out the one type of current, because there are two variables, we can't not to obtain solution, we should have two equations here. So let us simplify to one here. Since we already know equation for IE, just now we have derived, right? You can see here, where is that equation? Here, IB is equal to IE divided by 1 plus beta. That equation can be substituted here. Okay, so you can see here IB in place of IB, we are substituting IE divided by 1 plus beta. I also told you reason why we are substituting this. There are two, one is base current and other one is emitter current. There are two variables are there. So we have to convert this base current in terms of emitter current. So that's why we substitute in place of IB as IE divided by 1 plus beta. Now you can see once we do that, we have a emitter current here and emitter current here. There are two terms that contains emitter current here. Now I can take out emitter current as a common factor. If we do that from the second term and the fourth term, we get IE as a common factor and RE is left out here in this fourth term, and in the second term RB divided by 1 plus beta is left out here, and rest all terms we can transfer to the right hand side. Minus VBB becomes here plus VBB, as you can see here, plus VB becomes minus VBE. Okay, now we will retain IE on left hand side and send all these things to the denominator of this right hand side here. So IE is equal to now VBB minus VBE divided by RE plus RB divided by 1 plus beta. So now we got an expression for the emitter current, okay, of this classical discrete bias circuit arrangement here. This equation we got it here. Okay, so here straight away we may not we are unable to get this IC, we got IE, and look at here, there is this current IC and IE, they are going to be equal. Okay, for any transistor these two currents will be approximately equal, since gain alpha, what we say, it's very small. Okay, so that's we are highlighting in the next. Here for the time being you can remember this equation here, IE is equal to VBB minus VBE divided by RE plus RB divided by 1 plus beta. Again you can apply, since this is equal approximately, this IE will be equal to IC also. Okay, so we got now one of the operating point. What is operating point of a BJT? It is VCE and IC. This is the operating point. This is also called as a Q point. Okay, operating point. So we got one of the coordinate of operating point IC. The expression is given here. Okay, this is approximately, not exactly. Okay. Now let us apply KVL to the collector emitter loop and find out another coordinate of operating point. Go back to the circuit and apply KVL to the collector emitter loop. This equation is as shown here. There are three elements, one is two resistors, one is BJT. So we start with supply and end with ground. So minus VCC IC times RC, that is the voltage drop across RC. So plus VCE, that's the collector emitter voltage drop, and finally we have voltage drop across emitter resistor, which is IE times RE. So IE times RE, that's equal to 0. So this is the equation. Once we apply KVL to collector emitter loop, we get this equation. Same equation I will be showing here. This is the equation, and now we want this first coordinate of the operating point, which is VCE. So VCE equals now VCC minus ICRC minus IERE. So this operating point is also very important, because this operating point is just, it's a mid of our active mode, active region, what we said. If you recall the transfer characteristics, okay, so this operating point lies in the active region of a transistor. Okay, and now any change of this VC and IC leads to the change of the Q point, and transistor move into other regions like cutoff and saturation region here. Now we should identify carefully this VC and IC and what factor they depend upon, and if you can minimize those variations, definitely the circuit becomes a very good bias circuit here. In front of you there is an expression here, which you can see IC is now depends upon several things, right? Look at this, each and every term we have derived here. Okay, and also look at VCE equation also we have here. Okay, carefully if you observe this equation, they depend on several parameters here. Now irrespective of this variation of these parameters, what is this VC and IC is dependent, if you can minimize those variations, that means operating point will be stable in the active region, and device will perform very good amplification here. Okay, so here in this point what I showed here is IC is equal to alpha times IE. Alpha is very little small value, so this I told here IC and IE both are equal approximately. Okay, now let us see now this IE expression. If you observe this IE expressions, we have detailed analysis on this. IE expression now depends on IE is this is sensitive to the beta, I can see here, and even it has got a VBE here. Okay, so this, let me write it like this simply for simplicity. IC, IE or IC, IE, which is also approximately equal to IC. Now this is a function of I am just putting variables here. One is VBE, which is in the numerator here, and the denominator also you can see there is a beta. Okay, that means this IC or IE, which is the output DC collector current or output DC emitter current. Now it is a function of this VBE and beta. Now any change in VBE leads to the change of IC. Any change in the value of beta leads to a change in the value of IC. Now question is, how do we manage this? You have in front of you the mathematical expression like this. Now question is, I will be asking you now is, can we make IE or IC independent of this? Just think about that. Now it is I written here a function that they are related to each other. That's why I put here f, which is a function here. Now question is, now can we make this IC independent of VBE, or can we make this collector current, DC collector current, which is output current in the bias circuit, independent of the variations of beta? The answer to that is as shown here. There are two conditions here. I will just go through that. Just remember this. If you can set up a condition like this, what is the first condition? I must make VBB far greater than VB. And also second condition is I must choose a emitter resistor which is far greater than this RB divided by 1 plus beta. And by having these two assumptions in the IE equation, what changes are going to happen? Just look at this. This is the IE equation here. If I assume that VBB is greater than VBE, this VB numerator term, this VBB is greater than VBE, that means this term can be neglected, right? Since VBB is larger compared to VBE for the first condition. Second condition you can see here, RE emitter resistor is greater than RB divided by 1 plus beta. Look at this here also. The first term is greater than the second term here, RB divided by 1 plus beta. That means second term becomes very small compared to the first term here, emitter resistor. So therefore the second term also can be ignored. Now look at what happened to our IC equation now, if I do these two assumptions. Now final expression for IE has become now, look at this, we are only have here VBB in the numerator. Since VBB is larger than VB, we ignored this VB has become very small. And with second assumption, since RE is going to be very much greater than this RB divided by 1 plus beta, so second term becomes very small, I neglected it. So IE now becomes equal to VBB by RE. Now is this a good solution? With these two assumptions, let us call this as assumption 1 and this as assumption 2, what we are able to get? We are able to get emitter current or collector current, even though I have not shown here the collector current, both are approximately equal. They are equal to VBB divided by RE. That means there is no base emitter voltage term here, there is no beta term here. Once we establish, assume these two conditions here, the emitter current or collector current has become independent of base emitter voltage and independent of the beta value here. Of course, the circuit is with this kind of assumptions, it's a fantastic circuit, it's a beautiful circuit, bias circuit it is. But let us see what other challenges we have by doing these assumptions. Okay, so that part will be taken in the next class. Any questions so far?
No, sir.
I hope you have understood the contents that we have covered in the today's class. Next class we will start with these assumptions and see what challenges we have by assuming this, what other side effects we have, in the sense what other drawbacks we have by doing these assumptions. I also told you that with this kind of assumptions the circuit becomes very good, a beautiful bias circuit. But now in the next class I will be discussing with this kind of assumptions what other drawbacks we have, the issues or challenges we are going to discuss in the next class here. With that I will stop at today's class, and next class I will be continuing with the same the topic.